Hello, welcome back. Today we're doing the third and final installment of the video tutorials on Chapter 10, Section 5, Testing Convergence at Endpoints. We'll work through some examples today, go over how to find intervals of convergence, and then go over a general procedure for determining convergence. When a power series of the form sum n equals 0 to infinity cn x minus a to the n converges, to figure out where it converges, we start by using the ratio test to find the values of a for which the series converges absolutely. Ordinarily, it's an open interval, r to the left and to the right of a. In some instances, the series converges for all values of x, and in rare cases, it converges only at x equals a. Once we've found the interval of convergence, we next test for convergence or divergence at each endpoint. The ratio test doesn't help us at those points. At that point, we need either a comparison test, the integral test, or the alternating series test. If the interval of absolute convergence is from r to the left of a to r to the right of a, conclude that the series diverges even if it does not even converge conditionally for all points outside of that interval. So let's look at an example, or actually 4 examples. So example 6, the convergence of your knowledge about convergence. Showing quite a sense of humor there. Gee, math people really can be funny when they want to. Anyway, here are 4 series. We want to find the radius of convergence and the interval of convergence, and then we want to identify the values of x for which the series converges absolutely and conditionally. And we'll look at these one at a time, starting with A. So we always want to begin with the ratio test, and that'll find the interval of convergence and also the radius. Most of the time from now on, I'm just going to, instead of dividing an plus 1 by an, I'll be multiplying an plus 1 by the reciprocal of an, which is what is going to happen in the next step. I'm now going to simplify and do a little cancellation. So the limit of the ratio is the absolute value of x squared, and of course by the ratio test, this series will converge when the absolute value of x squared is less than 1, and you should know that that's when x is in between -1 and 1. So that's the interval of convergence, and the radius of convergence is 1. So now let's test the endpoints. To test the endpoints, -1 and 1, you substitute them one at a time into the original series. If you factor a half out, this becomes the alternating harmonic series. So this would actually converge conditionally at -1 to half of the natural log of 2. Now let's check 1. Well, at 1 you get exactly the same expression, 1/2 minus 1/4 plus 1/6. So this is an example of a series that converges conditionally at its 2 endpoints. Converges absolutely everywhere in between the 2 and diverges outside of -1 and 1. So to answer all of their questions, the interval of convergence is -1 to 1. It converges conditionally, -1 to 1. It converges, I'm sorry, I said that wrong. It converges absolutely from open -1 to 1. It converges conditionally at -1 and 1. All right, and the radius of convergence is 1. Let's take a look at example B. Okay, for me, I just look at this and that looks like e to the 10x from my knowledge of e to the x's Taylor series. So it should converge for all real numbers, but let's go through the work and confirm that. We've looked at one like this before. For any value x, no matter how large, eventually 10x over n plus 1 will get smaller and smaller and smaller. even if x is 1,000, n plus 1 will get above 10,000, and then the limit will start dropping below 1 and eventually become 0. So since the limit of an plus 1 over an is 0, which is less than 1 for all real numbers, the interval of convergence is negative infinity to infinity, and it converges absolutely for everywhere. The radius of convergence is infinite. Let's take a look at the next example. This one has nothing in the denominator to make it smaller, but the numerators keep getting bigger and bigger and bigger. It smells like trouble. So let's go ahead and check out what's happening with this one. We apply the ratio test. Now let's look at this last expression. If x is negative 1, then the expression inside the absolute value is 0 for any n at all, and then of course that's going to converge. But if x is any number at all besides negative 1, then the absolute value of x plus 1 is going to be some small positive number, and as n grows to infinity, n plus 1 times a small positive number goes to infinity. So this is that weird example that only converges at its center. So this is that third example. We had one with a fixed interval of convergence. We had one that converged for all real numbers, and here's an example of a series that only converges at its center. I wonder what the last example will bring. So here the numerator seems to be growing at a normal rate, and the denominator is growing fairly slowly. Let's apply the ratio test. So we found that the limit of the absolute value of a sub n plus 1 over a sub n is the absolute value of x minus 3. And setting that specifically less than 1, we find that the interval of convergence is from 2 to 4. Remember, you can read that absolute value as x is less than 1 unit from 3. So now let's test the endpoints. If I plug in 2, I get the following series. If you factor negative a half out of this, you get the alternating harmonic series. So this converges conditionally at 2. Let's go ahead and plug in the other endpoint, 4. Get a half plus a fourth plus a sixth, or 1 over 2n. So if I factor a half out, this is the harmonic series and diverges. So the answers to the questions: what's the interval of convergence? What's the radius of convergence? What is the region on which it converges absolutely? And where does it converge conditionally? And that's the end of this exploration. So now a nice little chart that summarizes step by step how you go through and test for convergence and look at convergence. So let's step our way through it. We're given a series and we have to figure out, does it converge or not? We start with the nth term test. Remember, the nth term test is a test for divergence. You can't use it to test for convergence. But if the limit of the nth term is not 0, bang, you know right away this series diverges. If the limit of the nth term is 0, or you're not sure, maybe it's 0, next thing look at, hey, is that a geometric series? Well, then I can just say that if the absolute value of r is less than 1, it converges to a over 1 minus r, and if the absolute value of r is greater than or equal to 1, it diverges. All right, so suppose that it's not a geometric series. The next thing to look at is, does it have the form sum 1 over n to the p? If so, we can apply the p-test. It'll converge if p is greater than 0 and diverge if p is less than or equal to 0. Suppose it doesn't have that form. Well, look at the sum of the absolute values. If that converges, then you can apply any one of the comparison tests, the integral test, the ratio test, or the nth root test. Remember that if a series converges absolutely, the original series converges. Next, and this is really important, that if the terms alternate in sign, get smaller and smaller with a limit of 0, then we know that by the alternating series test, not only is it going to converge, but we can put an error bound on it. If none of that works, well, you're kind of on your own. Try clever stuff, look things up. There are a bunch of other tests, but we didn't cover them in this chapter. Anyway, that's the end of chapter 10. There's some good stuff in here. Some of this was on the AP for this year, some of it isn't, but it's all interesting and all worth looking at. If you want, you can take the practice chapter 10 test. A couple of you have. If you're interested in doing a chapter 10 assessment, let me know and I'll write you one. But for now, stay healthy, stay entertained, stay friendly with the people you're sheltering with. And I miss you guys, and I'll start in chapter 11 next. All right, bye-bye.